Welcome to this video on basic probability. After watching this video, you will be able to define the terms experiment, trial, event, outcome, sample space, and probability model. You will be able to identify a trial, event, outcome, and sample space given the type of experiment being performed. You will be able to state the equation used in the classical method of probability, create a probability model, and find the probability of a simple event. You will also learn how to interpret the probability of a simple event. For an introduction to probability, please watch my video entitled Introduction to Probability. Let's get started. Here's some probability vocabulary. An experiment is any process that can be repeated and in which the results are uncertain. In general, each occasion upon which we observe a random phenomenon is called a trial. At each trial, we note the value of the random phenomenon, and we call that an outcome. When we combine outcomes, the resulting combination is called an event. The collection of all possible outcomes is called the sample space. Vocabulary example 1. Suppose you roll one six-sided die. Give an example of a trial, an outcome, an event, and a sample space in this scenario. If you want, you can pause the video, write down your thoughts, and then unpause it to see if you are correct. In this example, a trial is every time you roll the die. If you roll the die once, that is one trial. If you roll the die twice, then you have done two trials. Outcome. The outcome of the trial is whatever the die happens to land on. For example, if the die lands on a 1, then the outcome is 1. If the die lands on a 2, then the outcome is 2, and so on. Note that there's only one outcome for each trial. Event. An event combines multiple trials. For example, rolling a die twice and having the outcome be 6 both times would be an event. Sample space. The sample space is the set of all possible outcomes. So, in this case, the sample space would be 1, 2, 3, 4, 5, and 6. We could also represent that visually by drawing pictures of the 6 faces of a die. Example 2. Suppose you pick a card out of a standard deck of 52 cards. Give an example of a trial, an outcome, an event, and a sample space in the scenario. In this case, the trial would be choosing a card. The outcome is whatever card you pick. So, for example, let's suppose you happen to pick the 8 of diamonds. That would be your outcome. Event. An event combines multiple trials. For example, picking 2 cards that are both aces would be an event. Sample space. The sample space is the set of all possible outcomes. As you can see here, we've created and listed the sample space visually by showing pictures or images of each card in the deck of cards. Basic probability. The classical method probability formula states that the probability of an event is the number of ways that the event can occur divided by the total number of possible outcomes. Example 1. Suppose you roll a 6-sided die with the numbers 1, 2, 3, 4, 5, and 6 on the faces of the die. What is the probability of rolling an even number? The ways that the event can occur, in other words, the number of ways that we can get an even number, are that we could get a 2, a 4, or a 6. So there are 3 different ways that we could roll an even number. Remember, the set of all possible outcomes, or the sample space, is 1, 2, 3, 4, 5, or 6. So there are 3 ways the event can occur, and there are 6 possible outcomes. Therefore, the probability of rolling an even number is 3 over 6. We can reduce this to 1 over 2, or 0.5. Let's interpret this probability. If we were to roll a die 100 times, approximately how many times would you expect to have the face value of the die be even? So in order to answer this question, we can use the formula. Probability times the number of die rolls is the approximate number of times the event is expected to occur. In this case, our probability is 0.5, and we're rolling the die 100 times. So we would expect about 50 of those die rolls to be an even number. Let's do another example. Suppose there are 10 marbles in a jar with the colors as follows. There's 1 white marble, 4 blue marbles, 2 pink marbles, and 3 yellow marbles. Use the basic probability formula to find the probability of choosing a white marble, a blue marble, a pink marble, and a yellow marble. Pause this video, write down your answers, and then unpause the video to check yourself. Remember, the probability of an event is the number of ways that the event can occur divided by the total number of possible outcomes. One way to organize this information is to use a probability model. A probability model lists all the possible outcomes, as well as the probability of each outcome. Let's start to fill this out. There is one white marble, so that means that the probability of choosing a white marble is 1 out of the total number of marbles. If you count, there are 10 total marbles, so the probability is 1 over 10. There are 4 blue marbles, so the probability of picking a blue marble is 4 over 10. Likewise, there are 2 pink marbles, so the probability of a pink marble is 2 over 10, and there are 3 yellow marbles, so the probability of choosing a yellow marble is 3 over 10. Remember, in a probability model, the probabilities should always sum to 1 or 100%. If they do not, then you are not working with a valid probability distribution. Notice that we expressed all of these probabilities as fractions that were unreduced. There are other ways that we can express probabilities. Specifically, fractions can be reduced, and also you can use decimals or percents to represent probabilities. Let's do that. Pause the video, see if you can complete the chart, and then unpause the video to check your work. Let's look at our reduced fractions. 1/10 cannot be reduced, so it does not change. 4/10 can be reduced to 2/5, 2/10 can be reduced to 1/5, and 3 over 10 cannot be reduced. In order to get a decimal, all we have to do is type the fraction into our calculator. Remember, the fraction symbol is the same as the division symbol. So 1 over 10 becomes 0.10, 2/5 or 4/10 is 0.4, 2/10 or 1/5 is 0.2, and 3/10 is 0.3. To convert from a decimal to a percent, we simply multiply by 100%, and we have percents of 10, 40, 20, and 30. If you picked a marble out of the jar 100 times, replacing the marble every time, how many times would you expect to get a blue marble? Pause the video, write down your answer, and then unpause it to see if you are correct. Remember, the probability of picking a blue marble times the number of die rolls will give you the approximate number of times the event should happen. So in this case, remember the probability of a blue marble is 0.4. Multiplying that by 100 times, we get about 40. Remember, you're always going to have sampling variability, so the chances are we're not going to get exactly 40 marbles out of 100, but the number should be somewhere close to 40. Example 3. Suppose you pick a card out of a standard deck of 52 cards. What is the probability of choosing a red card? Pause the video, write down your answer, and then unpause it to see if you are correct. As you can see, there are 26 red cards and a total of 52 cards in a deck. So the probability of choosing a red card is 26 over 52, or 1/2. You could also express this as a decimal or percent by saying that your probability is 0.5 or 50%. Example 4. Suppose you pick a card out of a standard deck of 52 cards. What's the probability of choosing a club? If you are unfamiliar with cards, this symbol represents clubs, this symbol represents spades, this is hearts, and this is diamonds. There are a total of 13 clubs out of a total of 52 cards in the deck. Therefore, the probability of choosing a club is 13 over 52, or 1/4. We could also express this as a decimal or percent by saying that the probability is 0.25 or 25%. Suppose you pick a card out of a standard deck of 52 cards. What is the probability of choosing a face card? If you are unfamiliar with cards, face cards are those cards with a face on them. Specifically, they are jacks, denoted by a J, queens, denoted by a Q, and kings, denoted by a K. So we could rephrase this by asking, what is the probability of choosing a jack, queen, or king? Pause the video, write down your answer, and then unpause it to see if you were correct. There are 12 face cards, so the probability of choosing one of these cards is 12 over 52, which reduces to 3/13. This is about a 23% or 0.23 chance. In each of the previous examples, we assumed that every outcome listed in the sample space was equally likely. So, for example, in our marble experiment, we assumed that each of these marbles had an equal probability of being chosen. Even though there's a different proportion of different colors, any of the 10 marbles are just as likely to be chosen as any of the other ones. Likewise, in our card example, we assumed that every single card in the deck of cards was equally likely to be chosen. So again, in all of these examples, we're assuming that each sample space outcome is equally likely. Do you think this will always be the case? The classical method of computing probabilities requires that every outcome listed in the sample space is equally likely. If this is not the case, then the classical method of probability cannot be used. Here's a question. If you roll 2 dice, are the outcomes of getting dice whose spaces sum to 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12 equally likely? Pause the video, write down your thoughts, and then unpause it to see if you're correct. Before we can answer this question, it is helpful to draw or list the sample space of this event. Remember, the sample space lists all possible outcomes. Here's the sample space for rolling 2 dice. Does it look like what you thought it would? It's important to observe that in listing the sample space, order matters. For example, the event of rolling a 1 and then a 2 is different from rolling a 2 and then a 1. Even if you roll the 2 dice at the same time, the 2 dice are different. To illustrate this concept, the sample space shows the dice as 2 different colors. Now, let's look at this new sample space and ask ourselves the question, are the outcomes of rolling a 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12 equally likely? What do you think? These outcomes are clearly not equally likely because, for example, there are many more ways that a person could roll a 7 than ways that a person could roll a 12. A person to get a 7 could roll a 1 and a 6, a 2 and a 5, a 3 and a 4, a 4 and a 3, a 5 and a 2, or a 6 and a 1. Conversely, there's only one way to get a pair of 6s or a 12. However, it's important to note that we do assume that each of these 36 outcomes represented in the sample space are assumed to be equally likely. Example 6, rolling 2 dice. Suppose you roll 2 dice. What is the probability that the sum of the numbers on the dice is 4? Pause this video, work the probability out, and then unpause it to check your work. To determine the probability of rolling a sum of 4, all we have to do is circle all of the outcomes in the sample space that represent a sum of 4. So there are 3 ways to do this. We could get a 1 and then a 3, a 2 and a 2, or a 3 and a 1. Since there are 36 possible outcomes, the probability of rolling a 4 is 3 over 36, which reduces to 1/12, or about 0.08. We could also say this is about 8%. Let's interpret this probability. If you rolled a pair of dice 1,000 times, how many of those times would you expect the sum of the dice to be equal to 4? Remember, our formula is that we multiply the probability by the number of die rolls to find the number of times the event would be expected to occur. In this case, we have 0.08 times 1,000, which gives us 80. Therefore, the interpretation of this probability is that if we rolled a pair of dice 1,000 times, you would expect about 80 of those rolls to result in a sum of 4. You should now be able to define the terms experiment, trial, event, outcome, sample space, and probability model. You should be able to identify a trial, event, outcome, and sample space given the type of experiment being performed. You should be able to state the equation used in the classical method of probability, create a probability model, find the probability of a simple event, and interpret the probability of a simple event.